Welcome back to another lecture on OpenDSS-G. I'm Davis Montenegro, the creator of the tool. Today, I'd like to introduce you to the Load Allocation Assistant, a new feature added in version 7. This assistant provides a graphical interface for the existing load allocation algorithm in OpenDSS, making it easier to access, apply, and understand. By presenting the workflow visually, it helps users incorporate load allocation into their simulation setup with greater confidence and clarity. To begin, take a look at the power system displayed on the screen. The circuit model includes 3 substations, each supplying its own feeder. We'll start by identifying these feeders using the built-in feeder identification tool, which highlights the boundaries and origin of each one. After that, the island's heat map allows us to visually distinguish the feeders as shown on the screen. At this stage, the circuit has already been solved successfully. To open the Load Allocation Assistant, use its icon in the Automation subpalette or launch it through the Automation tool while in simulation mode. Once opened, the Load Allocation Assistant displays all energy meters installed across the circuit. In this case, the meters created automatically during feeder identification. The list shows the AMI measurements stored for each meter, along with the units in which those measurements were provided. In OpenDSS, energy meters can only store load allocation data in amps. However, the Load Allocation Assistant accepts additional units, including kilowatts, kilowatts and kVARs, kVAs, and power factor. Any required conversion to align with OpenDSS conventions are handled automatically within the assistant. Users can add, remove, or edit measurement values using the toolbar icons or simply by double-clicking the measurement they want to modify. The assistant also allows users to locate the measurement's position directly within the GUI, making it easier to verify where each value applies in the circuit. Additional configuration options are available as well. Users can specify the upstream transformer kVA rating to guide the allocation process, and they can define the power factor for the loads, either as a single value applied to all loads or differentiated by load class, such as residential, commercial, and industrial. The classification is determined using the load property values already present in the model, and can be specified by the user. Users can also specify the date and time for which the load allocation values are representing. Entering measurement values manually can become time-consuming, especially when working with large number of data points. In most workflows, these measurements already exist elsewhere, often stored in a database or can be exported as a CSV file. To streamline this process, the Load Allocation Assistant allows users to import measurement CSV files directly. The imported file should include the per phase values, the name of the measured element, which must match an element name in the circuit model, and the units. If a measurement already exists, the import process updates it automatically. If it does not, the assistant creates a new measurement in the form of a sensor. In the measurement tree, energy meters and sensors are represented with different icons, so users can easily distinguish between them. The next step is to define the transformer kVA rating upstream of the loads. This can be done in several ways. You may assign a single kVA value manually and apply it uniformly to all loads. Alternatively, you can let OpenDSS-G determine the value automatically by assigning the kVA rating of the transformer directly upstream of each load. A third option is to apply user-defined rules that specify how kVA values should be assigned across the system. All of these approaches are supported within the assistant. Once these values are assigned, click on the Run button to start the allocation process. A dialog will appear asking for the number of iterations for the allocation. The default number is 2, but it can be increased to enhance the allocation results if desired. Once the allocation process is complete, a new window appears showing the allocation results. This window summarizes the load allocation errors at each measurement point and provides a threshold control that helps users assess the quality of the allocation. Measurements with an error above the threshold are highlighted in red, while those within an acceptable range are shown in green. In this second example, the imported measurements are provided in kW and kVAR, and we will force the load power factor using a class identifier already defined in the model to distinguish between load types. After importing the measurement CSV file, you can see that the measurements tree updates automatically with new sensors representing the new added data. Even the existing energy meters previously storing values in amps are now updated with measures in kW and kVAR. Regarding power factor, we will assign separate values for residential, commercial, and industrial loads. These values are intentionally simplified for demonstration purposes. They are not meant to represent realistic operation conditions, and I fully expect them to break something in the process. Still, they serve well for illustrating how the assistant handles class-based assignments. In this model, residential loads are identified with the property class equal 1, commercial with class equals 2, and industrial with class equals 3. In the assistant, we add conditional rules that match these class identifiers when setting the power factor values. The assignment can later be verified using customized reports, which clearly reflect the power factor updates applied through the Load Allocation Assistant. When the allocation results look satisfactory, you can save them by clicking the Save icon in the toolbar. This action generates a .dss file containing all computed allocation factors. In addition to storing these values, this file also updates the OpenDSS temporal settings so they match the measurement date used during the allocation. Once saved, the file can be integrated into the project either through the scripting tool or by manually adding it to the master script. I hope you found this lecture both clear and useful, and I look forward to having you join me for the next session. OpenDSS-G has grown into a flagship platform for exploring and showcasing the full power of OpenDSS, and for more than a decade it has helped thousands of users learn, experiment, and innovate through an intuitive graphical experience. Each year we push the boundaries of what a graphical interface for OpenDSS can be, bringing the engine's advanced capabilities to life with richer visualization, smarter workflows, and tools that can accelerate both research and real-world engineering. To amplify that momentum, we've introduced the OpenDSS-G roadmap, a dynamic community-driven space where users can vote for upcoming features, propose new ideas, and engage directly with the development team. It is designed to make your voice central to the evolution of the platform and to ensure OpenDSS-G continues to meet the needs of utilities, researchers, consultants, and innovators across the industry. As an open source project, OpenDSS-G thrives on collaboration. We invite users to share their perspectives, help shape priorities, and, if interested, join as contributors to advance the next generation of graphical tools for power flow simulation based on OpenDSS. Visit opendss.prodcom.com to start your journey helping to shape the future of OpenDSS and OpenDSS-G. Thank you.